Okay, so we just said, okay, within this, we have a positive rotational velocity and a negative rotational velocity because we said those things can have signs. We define positive as counterclockwise and negative as clockwise. So both halves of the cat, the front half and the cat hat, the cat hat, but the front half and the back half are rotating in opposite directions. So we still have this where we can have a zero angular momentum. And then we're looking at later on. So later on, when this front half is rotated and it's facing downwards, like the legs would be down there. It's a crude drawing, but that's okay. It worked out. Kind of gets the idea across. So the legs are kind of down there. It's facing where the cat wants it. So what we're going to do is the cat's going to stick its legs out, its paws out, increase that rotational inertia, which would decrease the angular velocity because it doesn't want to spin anymore. It's at the location that it wants. It's spun the amount of radians that it wants to spin. And then on the back side, the back paws now this time are going in, so it's going to decrease our rotational inertia and then increase our rotational velocity. So we're going to have a low I and then by default a large omega. So if we're kind of looking at this, we can look at conservation on the full scale and kind of the individual scales. So here we see, hey, in this first part, the front half of the cat, rotational inertia is conserved. It went from a low I to a low rotational inertia and a large angular velocity to a large angular velocity, a large rotational inertia and a low angular velocity. So momentum was conserved within that case. We still have the same rotational inertia as before. And then the back half, same thing, large I, low omega, low I, large omega. Then on the full scale, angular momentum is still conserved. We have this idea that the positive rotational inertia from the front half minus the rotational inertia from the back half still equals 0, just like it did before. So we have the front half's rotational inertia, or not rotational inertia, sorry, rotational angular momentum canceling out the angular momentum of the back half. So hopefully that was a little bit more clear, or it was more confusing. But so we have this idea that the front half and the back half are canceling each other out. When we increase that rotational inertia, our angular velocity goes down. We want to have angular velocity in order for our cat to go from legs up to legs down. So it needs to spin, it needs to undergo that rotation. So hopefully that was helpful. And next we're going to do some practice.